Alrighty tidy whitey undies. See part 1 of the datasheet first. It's actually an older version of the datasheet. But, for my intents and purposes, that may not matter. Also, omitted is the data memory and organization portion of the datasheet. If you want to see that, then check out my PIC10F200 video part 9. This following video attempts to read the remaining part of the datasheet I did not cover. Please see the microchip link to follow along with this audio. I didn't feel ambitious enough to sync up screenshots of the datasheet. Come on dude. I can't do all the work. I am partly offended. The page numbers referenced are the PDF page numbers, rather than those appearing on the bottom of the datasheet pages. I am the sillies today. So, before I begin I would just like to say, POO poopy POO poopy pants. Page 14. PIC10F2001. 4.3.2 Special Function Registers. The special function registers are registers used by the CPU and peripheral functions to control the operation of the device. The special function registers can be classified into two sets. The special function registers associated with the core functions are described in this section. Those related to the operation of the peripheral features are described in the section for each peripheral feature. Table 4:1, Special Function Register Summary. INDF TMROPCL Status FSR OSCAL GPIO KNO TRISCPIO Option. Legend dash equals unimplemented, read as 0, x equals unknown, 2 equals unchanged, q equals value depends on condition. Note 1, the upper byte of the program counter is not directly accessible. See section 4.7 Program Counter for an explanation of how to access these bits. 2. Other resets include external reset through MCLR, watchdog timer, and wake up on pin change reset. 3. See table 9-1 for other reset specific values. 4. PIC10F20412006 only. 5. PIC10F20412006 only. On all other devices, this bit is reserved and should not be used. Page 15. 4.4 Status Register. This register contains the arithmetic status of the ALU, the reset status and the page pre-select bit. The status register can be the destination for any instruction, as with any other register. If the status register is the destination for an instruction that affects the Z, DC, or C bits, then the write to these 3 bits is disabled. These bits are set or cleared according to the device logic. Furthermore, the to and PD bits are not writable. Therefore, the result of an instruction with the status register as destination may be different than intended. For example, CLRF status will dear the upper 3 bits and set the Z bit. This leaves the status register as 000 ULU. Therefore, it is recommended that only BCE, BSF and MOVUF instructions be used to alter the status register. These instructions do not affect the Z, DC, or C bits from the status register. For other instructions which do affect status bits, see section 10.0 Instruction Set Summary. Register 4:1, Status Register. Legend, R equals readable bit N equals value at POR. W equals writable bit 1 equals bit is set. U equals unimplemented bit, read as 00 equals bit is cleared X equals bit is unknown. Bit 7 PWF, GPIO reset bit 1 equals reset due to wake up from sleep on pin change O equals after power up or other reset bit 6 CWUF. Comparator wake up on change flag bit L1 equals reset due to wake up from sleep on comparator change O equals after power up or other reset conditions. Bit 5 reserved, do not use. Use of this bit may affect upward compatibility with future products. Bit 4:2, timeout bit 1 equals after power up, CLR-WDT instruction or sleep instruction O equals a WDT timeout occurred bit 3 PD. Power down bit 1 equals after power up or by the CLR-WDT instruction O equals by execution of the sleep instruction bit 2Z. 0 bit 1 equals the result of an arithmetic or logic operation is 0 O equals the result of an arithmetic or logic operation is not 0 bit 1 DC. Digit carry / borrow bit add with 1 equals a carry from the fourth low order bit of the result occurred O equals a carry from the fourth low order bit of the result did not occur sub of 1 equals a borrow from the fourth low order bit of the result did not occur O equals a borrow from the fourth low order bit of the result occurred bit 0 C. Carry / borrow bit add with sub of RRF or RLF. 1 equals a carry occurred 1 equals a borrow did not occur load bit with LSB or MSB, respectively O equals a carry did not occur 0 equals a borrow occurred. Note 1, this bit is used on the PIC10F200/206. For code compatibility do not use this bit on the PIC10F200/202. Page 16. 4.4 Status Register. This register contains the arithmetic status of the ALU, the reset status and the page pre-select bit. The status register can be the destination for any instruction, as with any other register. If the status register is the destination for an instruction that affects the Z, DC, or C bits, then the write to these 3 bits is disabled. These bits are set or cleared according to the device logic. Furthermore, the 2 and PD bits are not writable. Therefore, the result of an instruction with the status register as destination may be different than intended. For example, CLRF status will dear the upper 3 bits and set the Z bit. This leaves the status register as 000UUUU. Therefore, it is recommended that only BCF, SSP, and 4.5 option register. The option register is a 8-bit wide, write-only register, which contains various control bits to configure the timer ONVDT prescaler and timer 0. By executing the option instruction, the contents of the W register will be transferred to the option register. A reset sets the option 7:0 bits. Register 4 to 2. Option register. Note, if tries bit is set to 0, the wake up on change and pull up functions are disabled for that pin. Note, if the TOCS bit is set to 1, it will override the tries function on the talkie pin. Legend, R equals readable bit N equals value at POR. W equals writable bit 1 equals bit is set. U equals unimplemented bit read as 0 feet 0 inches equals bit is cleared X equals bit is unknown. Bit 7 GPWU, enable wake up on pin change bit equals disabled O equals enabled bit 6 GPPU, enable weak pull UPS bit equals disabled 0 equals enabled bit 5 TOGS. Timer degree clock source select bit 1 equals transition on talkie pin O equals transition on internal instruction cycle dock, FOSC/4 bit 4 toes. Timer source edge select bit 1 equals increment on high to low transition on the talkie pin O equals increment on low to high transition on the talkie pin bit 3 PSA. Prescaler assignment bit equals prescaler assigned to the WDT O equals prescaler assigned to timer degree bit 2 to 0 P52:0, prescaler rate select bits. Bit value timer degree rate WDT rate. Page 17. Oh baby. 4.6 OSCAL register. The oscillator calibration register is used to calibrate the internal precision 4 MHz oscillator. It contains 7 bits for calibration. Note, erasing the device will also erase the pre-programmed internal calibration value for the internal oscillator. The calibration value must be read prior to erasing the part so it can be reprogrammed correctly later. After you move in the calibration constant, do not change the value. See section 9.2.2 internal 4 MHz oscillator. Register 4 to 3, OSCAL register. Legend, R equals readable bit N equals value at POR. W equals writable bit 1 equals bit is set. U equals unimplemented bit, read as 0 feet 0 inches equals bit is cleared X equals bit is unknown. Bit 7 to 1 cal 6:0, oscillator calibration bits equals maximum frequency. Equals center frequency. 10,00000 equals minimum frequency bit 0 FOSC4, INTOSC/4 output enable byte, 1 equals INTOSC/4 output onto GP2 0 equals GP2/TAKI/COOT applied to GP2. Note 1, overrides TAKI/COOT control registers when enabled. Page 18. Hot Sexy. 4.7 Program counter. As a program instruction is executed, the program counter will contain the address of the next program instruction to be executed. The PC value is increased by 1 every instruction cycle unless an instruction changes the PC. For a goto instruction, bits 8 to 0 of the PC are provided by the goto instruction word. The program counter low is mapped to PC 7:0. For a call instruction, or any instruction where the PCL is the destination, bits 7:0 of the PC again are provided by the instruction word. However, PC8 does not come from the instruction word, but is always cleared. Instructions where the PCL is the destination, or modify PCL instructions, include move with PC, add with PC, and BSF PCB. Note, because PC8 is cleared in the call instruction or any modify PCL instruction, all subroutine calls or computed jumps are limited to the first 256 locations of any program memory page. Figure 4-5, Loading of PC branch instructions. Goto instruction. 870 PCII PCLIT foot I instruction word I. Call or modify PCL instruction 87 PCII reset to A. PCL. 1 instruction word. 4.7.1 Effects of reset. The PC is set upon a reset, which means that the PC addresses the last location in program memory. After executing movelu XX, the PC will roll over to location 0000H and begin executing user code. 4.8 Stack. The PIC10F200/204 devices have a 2 deep, 8-bit wide hardware push/pop stack. The PIC10F202/206 devices have a 2 deep, 9-bit wide hardware push/pop stack. A call instruction will push the current value of stack 1 into stack 2 and then push the current PC value, incremented by 1, into stack level 1. If more than 2 sequential calls are executed, only the most recent 2 random addresses are stored. A readlu instruction will pop the contents of stack level 1 into the PC and then copy stack level 2 contents into level 1. If more than 2 sequential readlus are executed, the stack will be filled with the address previously stored in stack level 2. Note 1, the W register will be loaded with the literal value specified in the instruction. This is particularly useful for the implementation of the data lookup tables within the program memory. 2. There are no status bits to indicate stack overflows or stack underflow conditions. 3. There are no instruction mnemonics called push or pop. These are actions that occur from the execution of the call and readlu instructions. Page 19. Oh, hot pulsating sensation. 4.9 Indirect data addressing, INDF and FSR registers. The INDF register is not a physical register. Addressing INDF actually addresses the register whose address is contained in the FSR register. This is indirect addressing. 4.10 Indirect addressing register file 09 contains the value 10H register file 08 contains the value 0. I'll load the value 09 into the FSR register. A read of the INDF register will return the value of 10H. Increment the value of the FSR register by 1. A read of the INDR register now will return the value of 0. Reading INDF itself indirectly will produce a. Writing to the INDF register indirectly results in a no operation. A simple program to clear RAM locations 10H1FH using indirect addressing is shown in example 4-1. Example 4-1. How to clear RAM using indirect addressing. Initialize pointer, to RAM, clear INDF, register, inc pointer, all done? No, clear next. Yes, continue. The FSR is a 5-bit wide register. It is used in conjunction with the INDF register to indirectly address the data memory area. The FSR 4:0 bits are used to select data memory addresses 0-1FH. Note, PIC10F200- do not use banking. FSR 7:5 are unimplemented and read as is. Figure 4-6, direct/indirect addressing. Direct addressing 4C. Location select L00H. Data OFH MEMR 50, 10H. 1FH bank 0. Indirect addressing 40. I1 location select. Page 20. Wo. Wowie. Oaga yet. Users. 5.0 I/O port. As with any other register, the I/O register can be written and read under program control. However, read instructions always read the I/O pins independent of the pin's input/output modes. On reset, all I/O ports are defined as input since the I/O control registers are all set. 5.1 GPIO. GPIO is an 8-bit I/O register. Only the low-order 4 bits are used. Bits 7 through 4 are unimplemented and read as O's. Please note that GP3 is an input-only pin. Pins GPO, GP1 and GP3 can be configured with weak pull UPS and also for wake up on change. The wake up on change and weak pull up functions are not pin selectable. If GP3/MCLR is configured as MCLR, weak pull up is always on and wake up on change for this pin is not enabled. 5.2 tries registers. The output driver control register is loaded with the contents of the W register by executing the tries instruction. A 1 from a tries register bit puts the corresponding output driver in a high impedance mode. A 10 puts the contents of the output data latch on the selected pins, enabling the output buffer. The exceptions are GP3, which is input only, and the GP2/Taki/Coot/FOSC4 pin, which may be controlled by various registers. See Table 5-1. Note, a read of the ports reads the pins, not the output data latches. That is, if an output driver on a pin is enabled and driven high, but the external system is holding it low, a read of the port will indicate that the pin is low. The tries registers are write-only and are set upon reset. Table 5-1, Order of precedence for pin functions. Priority GPO GP1 GP2 GP3 1 CIN plus CINF OSC4I/MCLR2 tries GPIO tries GPIO COOT 3-Taki 4- tries GPIO. 5.3 I/O interlacing. The equivalent circuit for an I/O port pin is shown in figure 5-1. All port pins, except GP3 which is input only, may be used for both input and output operations. For input operations, these ports are non-latching. Any input must be present until read by an input instruction. The outputs are latched and remain unchanged until the output latch is rewritten. To use a port pin as output, the corresponding direction control bit in tries must be cleared. For use as an input, the corresponding tries bit must be set. Any I/O pin can be programmed individually as input or output. Figure 5-1, PIC10F200/202/204/206 equivalent circuit for a single I/O pin. Data business WR port. Data latch CK. REG tries F tries latch IT. Reset. .VDD VSS RD port. Note 1, see Table 3-2 for buffer type. I/O pin. Part 21. Butt cheeks hard like concrete. Table 5-2, summary of port registers. Address name value on power on reset value on all other resets n/atrisk PON/a option 03H status 06H GPIO. Legend. Shaded cells are not used by LULTI registers, read as 0. Equals unimplemented, read as 0. X equals unknown, U equals unchanged. Q equals depends on condition. Note 1, if reset was due to wake up on pin change, then bit 7 equals 1. All other resets will cause bit 7 equals 0. 2, if reset was due to wake up on comparator change, then bit 6 equals 1. All other resets will cause bit 6 equals 0. 5.4 I/O programming considerations. 5.4.1 Bidirectional I/O ports. Some instructions operate internally as read followed by write operations. The BCE and BSE instructions, for example, read the entire port into the CPU, execute the bit operation and rewrite the result. Caution must be used when these instructions are applied to a port where one or more pins are used as inputs/outputs. For example, a BSF operation on bit 2 of GPIO will cause all 8 bits of GPIO to be read into the CPU, bit 2 to be set and the GPIO value to be written to the output latches. If another bit of GPIO is used as a bidirectional I/O pin, and it is defined as an input at this time, the input signal present on the pin itself would be read into the CPU and rewritten to the data latch of this particular pin, overwriting the previous content. As long as the pin stays in the input mode, no problem occurs. However, if bit 0 is switched into output mode later on, the content of the data latch may now be unknown. Example 5-1 shows the effect of 2 sequential read-modify-write instructions on an I/O port. A pin actively outputting a high or a low should not be driven from external devices at the same time in order to change the level on this pin. The resulting high output currents may damage the chip. Example 5-1, read-modify-write instructions on an I/O port. Initial GPIO settings. Note 1, the user may have expected the pin values to be PPOO. The second BCE caused GP1 to be latched as the pin value. 5.4.2 Successive operations on I/O ports. The actual write to an I/O port happens at the end of an instruction cycle, whereas for reading, the data must be valid at the beginning of the instruction cycle. Therefore, care must be exercised if a write followed by a read operation is carried out on the same I/O port. The sequence of instructions should allow the pin voltage to stabilize before the next instruction causes that file to be read into the CPU. Otherwise, the previous state of that pin may be read into the CPU rather than the new state. When in doubt, it is better to separate these instructions with the NOP or another instruction not accessing this I/O port. Part 22. Hot senestions lurking in trousers. Figure 5-2, Successive I/O operation. This example shows a write to GPIO followed by a read from GPIO. Data setup time equals where, IC equals instruction cycle, TPO equals propagation delay. Therefore, at higher clock frequencies, a write followed by a read may be problematic. Page 23. Oh mama. Wowza wowza. 6.0 Timero module and TMRO register. The timer module has the following features: 8-bit timer/counter register, TMRO readable and writable 8-bit software programmable prescaler internal or external clock select. Edge select for external dock. Figure 6:1 is a simplified black diagram of the TimerO module. Timer mode is selected by clearing the TOCS bit. In timer mode, the TimerO module will increment every instruction cycle. If TMRO register is written, the increment is inhibited for the following 2 cycles. The user can work around this by writing an adjusted value to the TMRO register. Figure 6:1. TimerO block diagram. Counter mode is selected by setting the TOCS bit. In this mode, TimerO will increment either on every rising or falling edge of pin talkie. The TOS bit determines the source edge. Clearing the TOS bit selects the rising edge. Restrictions on the external clock input are discussed in detail in section 6.1 using timer with an external clock. The prescaler may be used by either the TimerO module or the watchdog timer, but not both. The prescaler assignment is controlled in software by the control bit, PSA. Clearing the PSA bit will assign the prescaler to TimerO. The prescaler is not readable or writable. When the prescaler is assigned to the TimerO module, prescale values of 1:2, 1:4, 1:256 are selectable. Section 6.2 Prescaler details the operation of the prescaler. A summary of registers associated with the TimerO module is found in Table 6:1. Figure 6:2, TimerO timing, internal clock/no prescale. PC instruction fetch. Timed. Instruction executed. Parts 24. Oh sexy. I want some more. Figure 6:3. TimerO timing, internal clock/prescale 1:2. PC instruction fetch. More degree. Instruction executed. Table 6:1. Registers associated with TimerO. Address name IE value on power on reset value on all other resets 01 HTMRO. .n/a option n/a GPIO. Legend, shaded cells not used by TimerO. Equals unimplemented. X equals unknown. U equals unchanged. Note 1, the tries of the talkie pin is overwritten when TOCS equals 1. 6.1 Using timer with an external clock. When an external clock input is used for TimerO, it must meet certain requirements. The external clock requirement is due to internal phase clock synchronization. Also, there is a delay in the actual incrementing of TimerO after synchronization. 6.1.1 External clock synchronization. When no prescaler is used, the external clock input is the same as the prescaler output. The synchronization of talkie with the internal phase clocks is accomplished by sampling the prescaler output on the Q2 and Q4 cycles of the internal phase clocks. Therefore, it is necessary for talkie to be high for at least 2 TISC and low for at least 2 TISC. Refer to the electrical specification of the desired device. When a prescaler is used, the external clock input is divided by the asynchronous ripple counter type prescaler, so that the prescaler output is symmetrical. For the external clock to meet the sampling requirement, the ripple counter must be taken into account. Therefore, it is necessary for talkie to have a period of at least 4 TISC divided by the prescaler value. The only requirement on talkie high and low time is that they do not violate the minimum pulse width requirement of TTOH. Refer to parameters 40, 41, and 42 in the electrical specification of the desired device. Part 25. Hubba Hubba. 6.1.2 Timero increment delay. Since the prescaler output is synchronized with the internal clocks, there is a small delay from the time the external clock edge occurs to the time the timer module is actually incremented. Figure 6-4 shows the delay from the external clock edge to the timer incrementing. Figure 6-4. Timero timing with external clock. External clock input or prescaler output 2. External clock/prescaler output after sampling. Increment Timero. Timero. Note 1. Delay from clock input change to Timero increment is 3 TISC to 7 TISC. Therefore, the error in measuring the interval between two edges on Timero input equals plus or minus 4 TISC max. 2. External clock if no prescaler selected, prescaler output otherwise. 3. The arrows indicate the points in time where sampling occurs. 6.2 Prescaler. An 8-bit counter is available as a prescaler for the Timero module or as a post-scaler for the watchdog timer, respectively. For simplicity, this counter is being referred to as prescaler throughout this datasheet. Note, the prescaler may be used by either the timer module or the WDT, but not both. Thus, a prescaler assignment for the Timero module means that there is no prescaler for the WDT and vice versa. The PSA and PS2:0 bits determine prescaler assignment and prescale ratio. When assigned to the Timero module, all instructions writing to the TMRO register will clear the prescaler. When assigned to WDT, a CLR-WDT instruction will clear the prescaler along with the WDT. The prescaler is neither readable nor writable. On a reset, the prescaler contains all O's. 6.2.1 Switching prescaler assignment. The prescaler assignment is fully under software control. To avoid an unintended device reset, the following instruction sequence must be executed when changing the prescaler assignment from Timero to the WDT. Example 6-1, changing prescaler WDT. Page 26. Pantaloons. To change the prescaler from the WDT to the timer module, use the sequence shown in example 6-2. This sequence must be used even if the WDT is disabled. A CLR-WDT instruction should be executed before switching the prescaler. Example 6-2, changing prescaler. Figure 6-5, block diagram of the Timero/WDT prescaler. Note 1, TOCS. TOS. PSA. PS2:0 are bits in the option register. 2. Talkie is shared with pin GP2 on the PIC10F200/20212004/206. Part 27. OOI. 7.0 Timero module and TMRO register. The Timero module has the following features: 8-bit timer/counter register, TMRO readable and writable 8-bit software programmable prescaler internal or external clock select. Edge select for external clock from either the talkie pin or from the output of the comparator. Figure 7-1 is a simplified block diagram of the Timero module. Timer mode is selected by clearing the TOCS bit. In timer mode, the Timero module will increment every instruction cycle. If TMRO register is written, the increment is inhibited for the following 2 cycles. The user can work around this by writing an adjusted value to the TMRO register. There are two types of counter mode. The first counter mode uses the talkie pin to increment timer O. It is selected by setting the TOCS bit, setting the CMTOX bit and setting the CUTN bit. In this mode, timer will increment either on every rising or falling edge of pin talkie. The TOS bit determines the source edge. Clearing the TOS bit selects the rising edge. Restrictions on the external clock input are discussed in detail in section 7.1 using timer O with an external clock. The second counter mode uses the output of the comparator to increment timer O. It can be entered in two different ways. The first way is selected by setting the TOCS bit and clearing the CMTOX bit does not affect this mode of operation. This enables an internal connection between the comparator and the timer O. The second way is selected by setting the TOCS bit, setting the CMTOX bit and clearing the CUTN bit. This allows the output of the comparator onto the talkie pin, while keeping the talkie input active. Therefore, any comparator change on the CUT pin is fed back into the talkie input. The TOS bit determines the source edge. Clearing the TOS bit selects the rising edge. Restrictions on the external clock input as discussed in section 7.1 using timer with an external clock. The prescaler may be used by either the timer O module or the watchdog timer, but not both. The prescaler assignment is controlled in software by the control bit, PSA. Clearing the PSA bit will assign the prescaler to timer degree. The prescaler is not readable or writable. When the prescaler is assigned to the timer O module, prescale values of 1:2, 1:4, 1:256 are selectable. Section 7.2 Prescaler details the operation of the prescaler. A summary of registers associated with the timer O module is found in Table 7:1. Figure 7:1, Timer O block diagram. Page 28. Figure 7:2, Timer O timing, internal clock/no prescale. Figure 7:3, Timer O timing, internal clock/prescale 1:2. Table 7:1, registers associated with timer O. Value on address name power on all other resets. TMRO. GPIO. Option. GPIO. Legend, shaded cells not used by timer degree. Equals unimplemented. Note 1, the iris of the talkie pin is overwritten when TOCS equals 1. 7.1 Using timer O with an external clock. When an external clock input is used for timer O, it must meet certain requirements. The external clock requirement is due to internal phase clock synchronization. Also, there is a delay in the actual incrementing of timer O after synchronization. 7.1.1 External clock synchronization. When no prescaler is used, the external clock input is the same as the prescaler output. The synchronization of an external clock with the internal phase clocks is accomplished by sampling the prescaler output on the Q2 and Q4 cycles of the internal phase clocks. Therefore, it is necessary for talkie or the comparator output to be high for at least 2 disk, NA. X equals unknown. Equals unchanged. Small RC delay of 2 TTOH, and low for at least 2 disk. Refer to the electrical specification of the desired device. When a prescaler is used, the external clock input is divided by the asynchronous ripple counter type prescaler. So that the prescaler output is symmetrical for the external clock to meet the sampling requirement, the ripple counter must be taken into account. Therefore, it is necessary for talkie or the comparator output to have a period of at least 4 disk divided by the prescaler value. The only requirement on talkie or the comparator output high and low time is that they do not violate the minimum pulse width requirement of TTOH. Refer to parameters 40, 41, and 42 in the electrical specification of the desired device.